Hello, my name is Jurgis Grube. I am a representative of company Lightguide. I am R&D engineer here. And what we do, we are manufacturer of optical fiber and fiber bundles. And today I'm giving small talk about what we do in our bundle technology and regarding this our achievement in deep UV fiber bundle technology. Yeah. Okay. So motivation. So everybody knows that main purpose of optical fiber is to transport light from point A to point B. And usually to do that, we use two main type of fibers. We use water-free fibers, which are optimized to work in visual and near infrared spectral range. Or we could use UV fibers, which are optimized to work in UV and visual spectral range. But more and more people, companies, customers are asking for fibers which is specially developed and we could use, and they want to use them in the below 260 nanometers. This is when working with a deuterium lamp or using neodymium YAG forced and fixed harmonics lasers. So if we use typical UV fiber, then it is well known that during this fiber irradiation, these fibers became darker and darker in some spectral region, and that is because we create mainly two types of defects in this fused silicon material, which is one is non-bridge oxygen hole with absorption band around 264 and 630 nanometers, and E prime center with absorption around 250 nanometers. And depending on the wavelength at which we are looking, then this darkening, reducing of transmission could be negligible. We cannot see that, or it could be very impressive. Like, for example, here at 250 nanometers, the transmission decrease only to below 5% from the beginning. So how do we measure this graphic to somehow analyze and quantify this effect? So we use this solarization measurement setup, which is actually quite simple. So we have deuterium lamp, we have shutter to open and close light source. We put our fiber or bundle to this deuterium lamp, and other end we put on the spectrometer. And then we do some irradiation within the time and obtain spectra. And then we calculate this induced, what we call solarization or induced attenuation level according to this formula, where POSS at time 0 is a fiber optic spectrometer signal at the beginning of the measurement. It means T0, first measurement. And here it's at arbitral time moment T. And then we do this solarization for 4 or 4.5 hours. And then we also can do some recovery measurements. That means that we close the shutter, wait some time, open shutter for a small period of time, typically 10 seconds. We do transmission measurements with spectrometer, close the shutter, and wait another time, 15, 30 minutes, 2 hours, and so on. And what we get, so in the end, we get two graphs. One is how induced attenuation levels that depends on wavelengths, or how this induced attenuation levels, solarization depends within the time. And we can see that for typical UV fibers, the main absorption arise at is around 230 nanometers, which means E prime center. And this attenuation level for 2 meter long fiber is quite high, 40 decibels on 2 meters. This is the same picture. What we can see is that 40 decibels on 2 meters means that transmission reduced below 5% within the time. So this is a big issue if you want to work in this deep UV spectral region, 260 nanometers and below. So what we could do, we could have specially made fibers, what we call DPV fibers. And for such type of fiber, we have induced this attenuation level lower, twice lower compared to typical UV fiber, but still it have high value. So how to reduce this maximum intent, this absorption maximum? Actually, it's nothing new. It's already known that if we have this fused silicon material, we could load this material with hydrogen, put some hermetic carbon layer to make this hydrogen live inside its core and clad material, then put in our case polyamide jacket. In this manner, we create some hermetic structure, hermetic fiber where hydrogen is in. Hydrogen in this fused silicon material react with these defects which are created using this irradiation time and neutralize them. So it means that this number of defects is quite low and this induced attenuation level is low. So here I can show you this induced attenuation level for DPV fiber, what was in the previous graph, around maximum is around 7 decibels. And for hydrogen-loaded fibers, this induced attenuation level at the same wavelength is around 20 times lower, 0.3, or even something less. So this is good achievement because we can reduce this induced attenuation level drastically, and this fiber is good to use in some actions what customer needs. And so we had one project where we wanted to build some where these fibers would need to be put in the laser system. And therefore, we use this, create this solarization measurements setup using 266 nanometer laser, neodymium YAG for harmonic lasers. We put our fiber or fiber bundle to this laser, other end to the energy sensor, and let them work. Laser shines, the laser light is passing through the fiber. We measure what is energy after that. To measure this induced attenuation spectra, so time to time we took this fiber or fiber bundle from this setup, put in the deuterium lamp as is shown here, and measure what is transmitted light in spectral. And then take this fiber or fiber bundle back, put on the laser, and continue this irradiation process. And when we do that with our fiber, hydrogen-loaded fiber, we saw that this induced attenuation level increased a little bit, but not drastically. This means that regarding if we are using deuterium lamp or powerful nanosecond pulse laser to 66 nanometers, the induced attenuation level is low. In this case, the laser energy was about 8.5 millijoules on small fiber, which was 200 micrometer core fiber. So we have fiber, good fiber. Then we wanted to make a little bit bigger active area, and to do that, we made some fiber bundles. We have in our company can make different kind of fiber bundles, fluid fiber bundles, clad fused bundles, hexagonal fused bundle, monolith fused bundle, and so on, according to some specific needs, what is needed. And here we use one method to make fiber bundle, which is what it means that we have a lot of these fibers stuck together, and if we are using fused technologies, this means that we are fusing them together to get as much possible active area as possible. That meaning increase this packing factor. And in this case, we make a bundle of lengths of 0.5 meters, 31 fibers, and for testing purposes, we made 3 types of bundles with different fusing lengths. That means that this light area is area which fibers are melted together, fused together. We make that such a fiber bundles, and then we put in our system to measure what is induced attenuation level. And we came to quite a harsh stop because when we do these induced attenuation measurements using the laser, we see that for hydrogen-loaded fibers, this induced attenuation levels is only about 0.5, 0.6 something. Then for these fused fiber bundles, it's back to the something 5 to 9 decibels. In addition, we can see this induced attenuation spectra shape differ because here we can see additional absorption bands start to appear. What is interesting, we can see that depending on what is the fused length, fused part length, then this induced attenuation level increase as this fused length increase. So we come to some issues which we need to overcome, and we need to understand what was happening because we have good fiber with good cellularization results using the laser, and then when we make some fiber bundles using some fusing technology, we see that there's a problem. So what we did, we took one fiber, we performed all the experiments which we did, all the procedures which we did with the fiber, which is usually done to make fused bundles. This means we apply heat and so on. And we see that for this typical hydrogen-loaded DPV fiber, which is one, the induced attenuation level compared to typical hydrogen-loaded fiber bundle is increased about magnitude of 2. And we also can see that this additional absorption bands start to appear. And it's this blue line is coming to similar to this black line, which was for fused band technology. So this means that we come to some conclusions that we cannot make fiber bundles with this hydrogen-loaded fiber bundles to work with the lasers, 266 nanometer pulse laser. And we needed to think some things what we could do, and what we could do, we came up with a new type of the fiber, what we call the stacked fiber bundles. So the problem is that we saw in this previous slide, fusing destroy good properties of hydrogen-loaded fibers. Other options would be to just take bare fibers and glue them together, but this is done for many times, and this is one of the options how to make fiber bundles by gluing them together. But the problem is that 266 nanometers is quite powerful lasers. The photon energy is quite high, and the glue which hold together the fibers will definitely, and we have done that, the glue is become destroyed when it is irradiated with this laser light. Okay, to overcome this obstacles, so we develop new fiber bundle technology, what we call stacked fiber bundle. So what does it mean? Stacked means that we took a lot of fibers, as many as we need. We stuck them together, and we managed to think how to hold them together. This is our secret. But what's more important is the surface of these fibers is clean. They are polished. They are clean. There is no visible sediments which could be burnt into these fibers when this powerful laser is irradiating them, and so on. So we create such a fiber bundle. This is with a lot of fibers. We also create with 31 fibers to compare with our fused bundles, and we can see that this induced attenuation level for this stack fiber bundle technology is low, below 0.5 decibels on. It's quite low compared to this fused technology and so on. What next? To see how this fiber bundle work in a greater period of time. So we create this fiber bundle, which you see in this picture. We use 266 nanometer laser with quite high energy, 12 millijoules. Energy density is over 60 millijoules on square centimeters. And there is, if I remember correctly, over 800 fibers, and we perform this irradiation. The laser was irradiated this fiber bundle for over 24 hours. And what we see is that induced attenuation level is only fluctuating in some small amplitude, which is within the measurement error. So what it means? It means that we can, using the stacked fiber bundle technology, we can make them to work with this powerful laser. Okay, what is one of the drawbacks of this technology is that we can see there's some clear non-use areas, so the packing factor is not high, around only 0.83 or something like that. But nevertheless, the transmission of such fiber bundles is high, over 70% in this case, and these transmissions remain the same before 24-hour solarization process and after 24-hour solarization process. The transmission remains the same, and that's the main point, that the transmission remains the same. The fibers do not degrade within the time when this 266 nanometers neodymium force harmonic laser is irradiate these fibers. So conclusion, so yes, we have created a new technology where we can utilize hydrogen-loaded fibers benefits as solarization resistance, and it is suitable to work with neodymium fourth or fifth harmonic lasers. And in the end, yes, we also tested that when we fuse these hydrogen-loaded fibers together, then this is also suitable to work with deuterium lamp, which compared to laser have lower output energy, and then it's this defect induction is not so high. Okay, that's it from my side. Are there any questions?